This is the read application node together. This time we're going to read together these application nodes from analog devices. It's AM-1057. Basically, it's an application note about how to use a accelerometer for inclination sensing to measure the tilt angle by Christopher Fisher. I'm using a MEMS analog devices accelerometer lately. I found this technical notes is very useful. It's well written. This is the introduction part, and not much new here, but I want to mention inclination sensing is use a gravity vector and its projection on the axis of the accelerometer to determine the tilt angle. So it's very important. We are based on gravity vector, and mainly it's the how the gravity project on the axis you want to sensing. And as the gravity is a DC acceleration, so any force that results in a DC acceleration will distort or corrupt the output signals, because according to Albert Einstein's general relativity, we cannot tell the difference between a gravity and a constant acceleration. Okay, let's directly move to the principle of tilt and inclination calculations versus single axis tilt calculations. It's pretty straightforward. If you have a horizon here, your gravity is pointing downward. If the tilt angle theta is the AX direction, so it's theta here. Okay, we know we are trying to measure, we try to decide the theta, but we're trying to measure is the projection of the gravity to the AX directions. Okay, so this is right angle here. So basically, we are trying to decide the vector, this vector here. So AX equals G times cosine this angle, right? So it's 90 degrees minus theta, which is G sin theta. Okay, this is the whole principle of the user gravity to measure tilt angles. Okay, so that's what we have here. The AX equals G times sine theta, the tilt angles. And if it's a single axis accelerometers, what is the sensitivity of with the angles? Okay, basically what's this plot here? What we have is here angle inclination and the output acceleration. Remember the equations ax g times sine theta. Okay, that's basically this plot about. If you look carefully here, we have zero acceleration here. We have zero inclination angles here. So it's basically the sine wave. Okay, we keep going like that. And the acceleration, it depends on your input angles, inclination, and the sine wave. So the sensitivity will be different. And zero inclination angles, we got zero gravity output, zero acceleration output. And at lower angle, roughly here, this is approximately a straight line. At lower angle, we have a relative higher sensitivities. That means the angle step corresponding to a bigger output acceleration steps here, right? If the angle increase from 0 degrees to 20 degrees, the acceleration will, the output will increase from here roughly to 0.4. Okay, but if the inclination angle approach to this peak, let's say closer to 90 degrees, okay, yes, this response is relatively flat. Okay, that means the sensitivity is lower at this 90 degrees or bigger angles here. As we can tell, for example, from 80 degrees to 100 degrees, that's 20 degrees inclination increases, but it's only cause very little change in output acceleration. So that should be careful. always remember that's this equation. Okay, now if we use a digital system to measure the acceleration, you need to know the digital, the least significant bit, how many bits your ADC is, and how many bits you can get, and what's the smallest bit should be to resolve the angle you want to measure. Okay, that's pretty straightforward here. You can use these equations to decide your resolution you need in the digital system, but we can just look this diagram here. Okay, so this is a plot of angle inclination in degrees and the incremental sensitivities. Basically, what's the sensitivity you need in term milli-G and per 1 degrees. This for 1 degrees increase of the inclination. So it's mg is milli-G, is not milligram. Okay, it's milli-G basically is 10 to minus 3 G. G is gravity, gravitational force. Okay, and this plot what means here. If you sense the inclination angle about 24 degrees, the output incremental sensitivity is about 16 milli-G per degrees and here. Okay, because small angle, you have a larger output, as we said before. However, if you add a 63 inclination angle here, so the incremental sensitivity drops to 8 milli-G per degrees. Okay, that means if you increase your angle from 63 to 64 degrees, the output only is about increase from some numbers plus 8 milli-G. It's very small numbers. If you just keep going, this output's incremental sensitivity will get even smaller. Okay. And as we said, at small angle, the angles, when the angle is small here, relative to the horizon, which is this direction, at a small angle, you have the highest sensitivity. And when the angle gets bigger, the sensitivity gets lower. Okay, this is a similar plot for 0.25 degrees increments. This is very small increments, okay? And same, we have an angle inclination you want to measure, and the output incremental sensitivity in term milli-G per 0.25 degrees. Similar ideas, small angle, higher sensitivity, and whenever, if you were, for example, for 23.5 degrees around these angles, when you plus 0.25 degrees, the incremental sensitivity change out in the output is about 4 milli-Gs per 0.25 degrees. Similar idea like here. Okay. So you can use these curves to decide based on the resolution you want, how many you want to resolve 1 degrees or 0.25 degrees, and you can decide what's the minimum milli-G, inter milli-G per least square bit you need. So you can decide how many bits ADC you want to use, so on. Or if you are good to sample the analog signals, you can decide your own ADC, what kind of ADC you should use. Okay, based on the equations we get above, the AX equals G sine theta, and the theta, the angle, which is the invert function of sine. Okay, sine minus 1, the invert function of sine. So it's AX divided by G. Sine theta is AX divided by G. Theta is arc sine AXG, which is the inverse function of G. Or you can write theta equals sine minus 1 AXG, which is different ways to write the inverse function of the sine. Okay, and if you know the Taylor expansions or Taylor expansion, you will know at smaller angle sine theta approximately equals to theta. But here, remember, theta is in radians, not degrees. If you know when you turn this degrees, from degrees into radius. How do you do that? So if you have degrees, divide by 100 degrees, 180 degrees times pi. Okay, that's how you turn this. If it's 30 degrees, you divide by 100 times pi. So it's in 30 degrees in angles, it will be pi divided by 6 in radius. Okay. If the theta in radius here, which is a very small angle, sine theta is roughly equal to theta. So this means ax g sine theta. Okay, at a small angle, small theta, you can just say ax equals g theta. This will make your calculations easier. So what we can look this curve here. This angle inclination and the calculated angle inclination. Okay, and so it's the inverse sine function is this line here. Okay, and the linear explanation based on here ax g times theta. It basically overlapped very well, roughly between minus 30 degrees to plus 30 degrees. So in your calculations, you can just basically use approximation, but it's up to you. You can also use a calculator exactly invert functions. Okay. Okay. So this is pretty much about the single axis tilt calculations. Let's later we can talk about the dual axis tilt calculations.